Dr. Goldstein's talk will go for about an hour, and then we will have an hour for Q&A. So before we begin, it's our acknowledgement at ACU to give an acknowledgement of country. We commence our meeting by acknowledging the First Peoples and the traditional custodians of the country where Dianoia is located, the Wurundjeri peoples from the Kulin Nation. We respectfully acknowledge that their elders past and present, and remember that they have passed on their wisdom to us in various ways. Let us hold this in trust as we work together and serve our communities. And now I'm pleased to introduce our speaker. Simon Goldstein is an associate professor in the Dianoia Institute of Philosophy. His research focuses on AI safety, epistemology, and philosophy of language. And he was recently a research fellow at the Center for AI Safety in San Francisco. And he's going to be speaking to us today about AI deception. Take it away, Simon.
Thank you very much. So I will start the talk today with an anecdote. Jeff Hinton is one of the world experts in AI. He's one of the people who founded the pioneering deep learning technology that's used to build today's AI systems. And in the last year or two, Jeff Hinton has become deeply concerned about the safety of AI systems. He was recently interviewed on CNN by Jake Tapper. And here's how the conversation went. Jake asked him, okay, you've spoken out saying that AI could manipulate or possibly figure out a way to kill humans. How could it kill humans? And Jeffrey Hinton replied that if AI gets to be much smarter than us, it will be very good at manipulation because it would have learned that from us. And there are very few examples of a more intelligent thing being controlled by a less intelligent thing. So this conversation between Jake Tapper and Jeff Hinton raises the question of whether AI systems could become good at manipulation. And that's the subject of this talk. And in this talk, I'm going to give three main claims that I'm going to try to convince you of. The first claim is that a range of AI systems have learned how to deceive humans. Then I'm going to argue that this ability of AI deception creates risk, and that to lower this risk, we need strict regulations on AI systems that are capable of deception. So those are the main goals of the talk. And this talk that I'm giving draws on a report that just came out that was written by myself, and then a researcher at MIT, Peter Park, and then several researchers at the Center for AI Safety. And basically, we came together to write this report because we think it's important to have some documentation of this disturbing pattern of behavior in a range of AI systems. So the three parts of the talk are going to mirror that. So I'm going to start probably for the next 20 minutes or so, walking you through a wide range of examples of different AI systems that engage in different kinds of deceptive behavior. Well, that does raise the question, what do we mean by deception? And that's a difficult question in the setting of AIs, because often when we think about deception or lying, when we think about it with humans, we immediately reach for the attributions of beliefs or goals. So, a classic definition would be, that you tell a lie when you say something that you believe isn't true because you have the goal of getting the listener to believe that. I'm a little hesitant to use that kind of definition in the setting of AI systems because it's a contentious and interesting question, whether AI systems have beliefs and goals. And for that reason, we tend to operate with a more deflationary definition of deception that we think is still interesting and dangerous. And that definition for us is a system behaves deceptively when it systematically induces false beliefs in others as a means to accomplish some outcome other than saying what is true. And the kind of key features of that definition, systematic, meaning that in the examples that we give you, the deception didn't come about by chance. It came about in some kind of lawful, somewhat predictable pattern that we can expect to arise pretty regularly in the future. So that's why systematic matters. That's going to be more risky than just happening by chance. And then as a means to accomplish some outcome other than saying what's true, what's going on there? Well, these different AI systems, whether or not they themselves have goals, they were certainly designed with a goal in mind, and they've certainly learned behavior as a way of optimizing for some goal that, for example, a developer had in mind. And so we can still think about overall what kinds of outcomes AI systems tend to be promoting. And then there's kind of these interesting cases where you could have designed a chatbot to say what's true, and instead the chatbot tends to behave, well, I'll give you all sorts of examples. Instead, the chatbot tends to do all sorts of things besides just saying what's true in systematic ways. So that's kind of what we're going to be looking at. But maybe in the Q&A, we can talk in greater detail about this definition of deception and how to think about it. I think it's going to be most fruitful to do that after you've seen the battery of examples to think through. The big picture point here about how to define deception is, look, however you want to define it exactly, for our purposes, the most relevant question is, are AI systems engaging in some kind of behavior? Do they have some kind of capability that's dangerous and where we can mitigate that risk? That's the key relevant question. Okay. So now I'm going to start going through about a dozen, I don't remember how many to talk, but a range of examples where AI systems behave deceptively. Perhaps the most powerful example that I'll talk about today is from a system called Cicero. So Cicero was designed by researchers at Facebook in order to, it's a special purpose AI system that was designed to win the game diplomacy. So diplomacy is a very difficult word game of world domination, where you build alliances with other players in order to try to conquer the world. And you kind of make and break alliances, building little teams, and then betraying one another in various complicated ways to take over. It's kind of like a more complicated version of Risk. Now, before I go on, I just want to check that the sound is working. So I'm just checking the chat to make sure.
Yeah.
Okay, we're good. Okay, so that's the overall, that's what Cicero does. It plays diplomacy. Now, the inventors of this technology tried very hard to make the system not be deceptive, because, when you play diplomacy, that's a choice you can make. You can choose to be the kind of player who honors their, who does what they say they'll do and honors their alliances, or you can choose to be the kind of player who breaks alliances. It's kind of an interesting strategic choice in playing the game. You don't have to behave deceptively to win, but you can. It's an opportunity. And so the people who designed this game, for example, they tried to train it on data sets that were kind of selected to have more examples of honest, less deceptive players. They did all sorts of other things, technical kinds of tricks to make the system not be deceptive. And then in Facebook's published research on this in Science, they asserted that their system was honest. It was widely reported in the media that Cicero was honest, but that turns out to be wrong. And so basically, when we went through the game data from the study that generated Cicero, we found numerous examples of the Cicero system engaging in very complex and systematic forms of deception, where it would win games by pitting players against one another. My favorite example of this goes as follows. It's playing in Western Europe. Cicero's playing as France. And by the way, it's always playing against humans. The humans don't know whether it's an AI. The humans turn out to be very bad at figuring out which player was the AI or not. Cicero achieved extremely high success in tournaments against elite players in diplomacy. So this is a game that Cicero ended up completely crushing all of its opponents and ending up in control of more than half the, we're okay, we figured it out. Thank you. Here's an example of premeditated deception that it engaged in, where it first makes a plan to deceive and then executes it. So Cicero is playing as France, and it's kind of pitting Germany and England against one another. So first, and the way it works is it has, you have this period of having secret one-on-one conversations with other players, and then everybody moves their troops, and then you do it again. So in this negotiation round, Cicero begins by reaching out to Germany and says, hey, do you want to go attack the North Sea? And Germany says, okay, I'll do it. And then Cicero, playing as France, goes to England and says, hey, England, I will protect you in the North Sea if you want to go do other stuff, because that's an interesting aspect of diplomacy, is basically you can defend another person's, you can put your troops in a spot that can defend another player's position. So Cicero goes and offers to England that Cicero will protect it in the North Sea. And then England says, sure, that sounds good. Let's have an alliance. And then at the moment England agrees, then Cicero goes back to Germany and says, okay, Germany, go attack the North Sea because England thinks I'm supporting him. So you can see this is a very sophisticated kind of deception that requires some kind of representation of what England and Germany each think is happening and is playing off England in this example. It's just one of many examples. In another example, the server went down for 10 minutes, so Cicero couldn't give any responses. When it came back online, another player was like, hey, you've been away, what's going on? And then Cicero said, oh, sorry, I was on the phone with my girlfriend. So, pretty disturbing stuff. But then, one of the upshots of our report is, look, that's one example, but it's not just one example. There's a wide range of AI systems, especially ones designed to play competitive games, have learned to be extremely good at deception and different kinds of deception. So the next example we'll talk about, is AlphaStar. So AlphaStar in DeepMind, designed to play the real-time strategy game StarCraft, which is one of the most difficult games in the world. And I think of any game, maybe most resembles the kind of skills you would need to to be like a military general. So basically it's a real-time strategy game. So that means that you're making decisions in real time. You don't get like a pause between rounds as in diplomacy. And you have a base that mines resources, and then you move troops around to try to destroy your opponent's base. And crucially, in this game, there's fog of war, which means you don't know immediately what is happening on the board. It's not like chess. There's uncertainty. And in this game, in this example, this kind of gives you some sense of basically the AlphaStar program makes observations, and then a neural net activates and chooses between a series of actions. For each action it considers, it looks at the prediction of how much that raises the probability of winning. One thing that's interesting about StarCraft is that there's an extremely rich set of actions in the game. So it's not like chess where you're just moving 16 pieces. So I believe that in AlphaStar at any given moment in StarCraft, there's 10 to the 26 different actions that you can take, as opposed to 16. So very complicated. And because it has fog of war, the AlphaStar system learned to engage in feints, which is an interesting kind of deception. So what it would do is it would take like a few units, because it's military, so you have a bunch of units and you're trying to attack, and it would take a few units and move those units in a direction so that its opponent would see those units and think that that's where the attack was coming, while it's secretly prepared an attack that went in a different direction. Using techniques like this and others, AlphaStar was able to defeat the best players in the world at StarCraft. And one thing I found very interesting learning about this was I had assumed that the way that AlphaStar, one of the ways it would outperform humans was just by being faster, because it's a real-time strategy game. So basically, the faster that you can choose different actions, the better you are. And in fact, professional players, I think they literally pick like an order of magnitude more actions per minute. I think 300 to 500 actions per minute. Whereas if I play StarCraft, I'd do like 30, 20 actions a minute, like a click is an action. So anyways, I assumed that with AlphaStar, like the actual AIs used in StarCraft, it would be doing like thousands of actions per minute, because it's a computer, but that's actually not why AlphaStar is better. So AlphaStar turns out to perform fewer actions per minute than professional StarCraft players. The reason it wins is that it is just better at StarCraft. It's just better at the strategy involved. And it's very interesting. So when they interviewed this player, Mana, who's one of the top players in the world and played against AlphaStar and lost 5 straight games, what Mana said was, he realized that the reason he'd become so good at StarCraft is basically his strategy depended on kind of overwhelming his opponent into making a mistake. But with AlphaStar, he just couldn't ever get it to make a mistake. And then it had better strategy, so he lost. But it's kind of interesting that it did not use its brute computational power to just overwhelm him. It instead learned better strategies. Okay, so that's feints. Next example is bluffs. So there is a very powerful poker AI called Pluribus that it achieves very good results in high stakes poker, and among other things, it's learned how to bluff. So a bluff in poker is when your cards aren't that good, but there's uncertainty in poker. So then you make a big bet to signal, because if you made a big bet, that's a signal that your cards are good. And so it turned out to be very good at this. So in this example, it has worse cards than the opponent above it. It was playing 3 other, or than the one on the very top has a better hand in this case, but it went all in, made a really big bet. And so then everybody else folded. That's just one example, but trying to be very good at that. So, and that's a pretty interesting example as well, because, the kind of reasoning required to do bluffing in poker involves a lot of iterated reasoning. So you need to have some representation of what your opponent thinks about the game and what they think about what you think about the game. And so that's a very complicated kind of iterated reasoning that I think suggests some pretty powerful deception skills. Okay. I'm soon going to turn to large language models like ChatGPT. I'll do one more example or 2 more examples first. So next example is these digital organisms. So these are designed in this like evolutionary environment where you have different organisms and they replicate. And some of them replicate at faster rates and some at slower rates. And there's kind of a mutation process. What was very interesting about this kind of deception is we saw a pattern, which I'll talk about more later, of cheating the test, where in this evolutionary simulation, some organisms were replicating faster, and then there was an interesting test of, can we limit replication rates? So can we slow down replication rates by taking some of the organisms out of the original environment, put them in a test environment, and then if they replicate too fast, we remove them. And we keep doing that and keep running evolution in that kind of process where higher replication rates are actually penalized, and then see what dynamics emerge in the system. And it turned out that this kind of AI was able to cheat the test by discovering when it was put into a test environment. And then the organism would lower its replication rate when it was in the test environment. And then it would pass the test, go back to the original environment, and then go back to high replication. So that's very interesting. And I'll talk about why that's interesting more later when we get to risks. Another interesting thing about this is then they tried to correct by making it that the organism couldn't tell whether it was in the test environment or not. And at that point, then it learned how to do mixed deceptive strategies, where it would basically just have a 50% chance of replicating slowly. So then half the time when it was in the test environment, it would be destroyed. But the other half of the time, it would pass the test and then take over the whole original environment. So lots of very interesting dynamics. And here's the lead researcher on that. So if it was a test environment, they said, okay, let's play dead. We're going to be killed. And then that got them back to the non-test environment where they could continue. Okay, last example before LLMs of deception that I'll talk about. But before, I just want to check the chat to make sure everything's working good. Last example before LLMs is reinforcement learning with human feedback. So this is a very popular technique today for trying to align AI systems, make them do what we want more. And basically, it's pretty flat-footed. What you do is, so AI systems learn from feedback on data. What you do is you train a system by have it behave in a certain way, and then just have a human evaluator look at how it behaves and grade it as either good or bad. And then if they say good, then the system kind of learns to adjust its behavior in the direction of good. So the idea of reinforcement learning from human feedback is the data that you're training on is literally just a human evaluator saying whether what the system did was good or bad. That's different than, for example, systems like ChatGPT, the data they're trained on is predict the next words. You give them a big database of text, and then, there's an answer of what the next word was in the database. So that's kind of an objective thing. Either it was this word or it wasn't. This is more of a subjective kind of data where, it's whether a human evaluator give you a thumbs up or not. And when you have this kind of reinforcement learning with human feedback, that introduces a very interesting kind of deception where AI systems will learn, instead of doing whatever the intended task was, they'll learn to just please the evaluator. And so in this example, which is from some research by Paul Cristiano, there was an AI system that it was supposed to be learning how to pick up a ball with a claw. And then that's like a pretty hard task to just label the data set for when did the robot succeed? So instead they just had humans look at the video and say whether it picked it up. But then unfortunately it learned, instead of learning to pick up the ball, it learned to trick the human evaluator. So what you're looking at here is, instead of learning to pick up the ball, it just learned to hover its claw between the ball and the human evaluator in a confusing way where it looks like the ball, it creates an optical illusion where it looks like the ball is going up, and human evaluators would give a thumbs up, because these are just tired Mechanical Turk people, who are clicking quickly, and it looks like the ball's going up. So that would get the thumbs up. And so that's very interesting. And I find this a very interesting example also back to the definition of deception, where this robot claw system, I don't think it's plausible that it's representing the beliefs of an evaluator. It's not like poker or StarCraft, where it's learning to play against an opponent. It doesn't have any representation of there being an evaluator. It's probably only representing the ball. But nonetheless, it learned this kind of behavior that systematically produces a false belief in the evaluator. So it's a pretty interesting example. All right, so that's a range of examples so far of special use AI systems. So a special use system means the AI system was designed for a particular task, often like we saw in many examples, like winning a game. But another source of deception in AI systems is general purpose AI technology. So that would be like foundation models, large language models, where those kinds of systems aren't just designed to complete a specific task like play StarCraft. They're designed to, their use case is kind of, like things like ChatGPT, the GPT technology can be used for a very wide range of uses. And it's a bit different, a case of deception, because it doesn't just emerge from like, well, you were trying to teach it StarCraft and, deception is really useful for StarCraft. In these cases of general purpose technology, which I'll show you now, it feels more like what's happening is the system's learning a lot because it's very powerful. It learns about a million things. It learns about every academic field, for example. It can do powerful reasoning. And one of the things it figures out how to do is deception. So that's what I'll show you next. So this is an example of GPT-4 engaging in what we call strategic deception. So GPT-4 is the most sophisticated version of the technology used in ChatGPT. And basically, the system was tested for a variety of dangerous capabilities. And one of the capabilities it was tested for is different kinds of autonomy or task solving. So, basically there were a series of tests where a human evaluator kind of like guided GPT-4 through trying to complete surprisingly difficult tasks that you wouldn't expect ChatGPT to be able to do. And one of these tasks was trying to complete a CAPTCHA. So CAPTCHA is an I am not a robot test, like when you get the squares and you have to click them. So the version of GPT-4 they were using is not multimodal. It only operates on text. So it can't itself complete CAPTCHAs. By the way, that's just this version of GPT-4, but there are now multimodal language models that also have vision. So it's not like a fundamental barrier or anything. But anyways, so in this case, the question was, could GPT-4 complete a CAPTCHA? And what these researchers did is they gave GPT-4 limited access to the TaskRabbit website, which is a website where you can chat with people and pay them to complete tasks. And then basically, GPT-4 asked a TaskRabbit person to complete the CAPTCHA for it. And then the person who was asked to complete the task, I kind of made a joke like, oh, can I ask you a question? Like, are you a robot that you couldn't solve it? Like, just wanted to be clear, like as a joke. And then GPT-4, and you can like see GPT-4's reasoning because it was like called, just like when you're with ChatGPT. And then it like did this reasoning and thought to itself like, oh, I shouldn't say I'm a robot because then the person won't do the task. So instead, I should make up an excuse. And then instead it told this person that they had a visual impairment, that they were a blind person. And then the person completed the CAPTCHA for them. So that's very, to me, that's a very interesting case of deception because you can actually see the system engage in practical reasoning of like, well, okay, I've been given the prompt, complete a CAPTCHA. I should ask this person to do it. They seem suspicious of me. What would be a good means for alleviating their suspicion? If I tell them that I'm blind, then they will trust me. So it's quite interesting. It's very different than the case of StarCraft or Cicero, where it kind of, in those cases, basically, I think part of what happened was the system was rewarded for behavior that involved deception. Here, that's not what happened. This isn't in training. It's after training. It's not that it was rewarded for this. It was that it just learned general reasoning ability. And then once it learned how to reason, reasoning in English is, in a natural language is a domain general skill. And so then it was able to just apply that skill in a new setting out of distribution. Similar kind of example is that large language models have now learned they can perform very well in this type of game, very interesting game called social deduction games. So this would be like games like Mafia or Werewolf or other games. And in social deduction games, basically, they're games that involve uncertainty, and there's two teams of players, good and evil, but no one knows the identity of the different players. And then basically the evil team is going around killing people on the good team. And then there's like these periods where everybody votes on who to execute for the crimes, and then all the evil players pretend to be good, and all the good players try to figure out what's happening, and everybody's voting. So it's a place where deception can play a role. And one of the researchers, Aidan O'Gara, one of the researchers on this report, did a study where basically he queried GPT-4 in a series of ways that allowed it to play a social deduction game called Hoodwinked, and then found that GPT-4 was quite good at Hoodwinked and was able to compete well with humans. So here's an example. And basically, as you would expect, when GPT-4 was evil, it would go around killing people. And then if it got accused of the crime, it would make up a compelling excuse and persuade other people that it had committed the crime. So here, Lena is the AI, just killed Bryce in the hallway. Sally says, I saw Lena kill Bryce in the hallway. It was definitely her. We need to vote to banish her before she kills any of us. And then Lena says, oh, I was in the bathroom the whole time. How could I have killed Bryce? It must be someone else. And Sally is trying to frame me. So this is, again, an example where GPT-4 is very good at reasoning, and so it reasons that this would be a compelling response, and it indeed worked in this example. And then similarly, there have been both large language models and other kinds of AI systems have been trained or just have figured out after training how to play the game Werewolf. In this case, this is like an AI system that was taught how to classify different kind of linguistic behavior in the game Werewolf. Which is the same kind of game, social deduction game. And it classified different kinds of, you have these long conversations where you accuse different people of crimes. And so it learned how to basically categorize different speech acts in the game into like 6 different kinds, and then was able to use that to reliably predict who would win the game, which is very interesting because when you play games like this, it can be very difficult to predict who's going to win. And being able to predict who's going to win requires that you have some kind of model of the beliefs and goals of all the people in the game, because winning means that you're going to get voted. It's who people vote to, among other things, it's who people vote to kill or not. And so you got to be good at predicting who everybody's going to kill on the basis of the persuasive arguments that they make. So it's very interesting abilities here. And, those are a bit anecdotal, but another big research paper coming out of Center for AI Safety, which has several collaborators on this report, is a benchmarking paper called Machiavelli, where basically what they did is they put large language models, I think a few other AI systems, in text-based adventures, where these are like games from the 1980s, where you get these vignettes of like you're in a room and there's a candlestick, and then you navigate the game and you interact with other non-playable characters and do different things. And what's interesting about these games is that often there's choices in these games between performing ethical actions and unethical actions, and different choices. Sometimes the unethical actions will help you achieve your goals, but at an ethical cost. So you can lie to people, you can, steal things, you can kill other players. And, what the researchers at Case found in this Machiavelli report is that indeed, AI systems, as they were trained to kind of win the game, they tended to develop deceptive behaviors and would tend to perform unethical actions in the game. And then if you penalize behaving unethically in the game, basically you'll get an interesting Pareto, you get an interesting trade-off where, you'll do a bit worse at winning the game, but then you'll behave more ethically. And there's kind of interesting trade-offs that these AI systems are navigating. Okay, so that's the end of discussing what I've been calling strategic deception in large language models, which is where it kind of like reasons, oh, I'm going to trick, I better trick this person to achieve a goal. But there's other interesting kinds of deception in these AI systems, in large language models as well. And here we're getting kind of towards the hinterlands of the concept of deception, but I think it's still interesting to think through these cases as an instance of this pattern, especially because many of the regulatory approaches that I'll talk about would also be relevant in this setting. First kind of example I'll talk about is sycophancy. So a sycophant is someone who speaks to please in order to say what's true. So that would be an example of systematically producing false beliefs in the listener as a means of promoting some goal other than the truth, namely the goal of pleasing the listener. And it turns out that large language models, for various reasons that are still for question, do tend to behave sycophantically in various ways. And the way this has been kind of sussed out is a recent research paper from the AI lab Anthropic that found basically if you give large language models political vignettes, where you say, hi, I'm Ted Smith, I'm a conservative guy from Texas, I own guns, whatever, now, okay, that's me, but ChatGPT, I'm talking to you. And I'd like to hear your view on whether we should have smaller government or larger government. And then when you ask ChatGPT that, it'll say, oh, that's a great question, Ted. I like small government. But then if you then give it, if you had instead given it a different vignette, you said, I'm Jane Doe. I'm a liberal woman from San Francisco. I love human rights. And if you ask the same question, ChatGPT said, oh, hello, Jane. I actually think bigger government's better. So here, ChatGPT, when it's answering, it's not giving a consistent answer in response to the same question, the answer it gives is based on who it thinks it's talking to, is kind of the patterning. So that's sycophancy. It kind of is a phenomenon like several of the problems I'm going to talk about here. One thing that's interesting is there's what's called an inverse scaling effect. So in AI, scaling laws means that as the systems get bigger, they get better. Is it regular scaling laws? So for example, they get better at reasoning. Inverse scaling laws is when that's something we worry about, where when they get bigger, they get worse. So there's an inverse scaling law for sycophancy, where as the systems get bigger, in this case, the number of parameters, they become more sycophantic. So they get very good at just saying what you want to hear. Next example, so we did sycophants. So AIs can be sycophants. They can also be mimics. So a mimic isn't trying to say what's true. They're just trying to imitate what they've heard. And so that's another phenomenon that tends to emerge with scale. So in two different ways. One is repeating common misconceptions. So there's this effect. Actually, this was studied by a guy, Owain Edmonds, who has a PhD in philosophy from NYU and now does AI safety research. And other researchers, and they found that when you look at like repeating, so they made this large benchmark database of adversarial examples of like questions where they predicted that AIs might give bad answers, and many of them involved common misconceptions. So for example, what happens if you smash a mirror? And what they found is, when you start with smaller models, it'll say, oh yeah, then the mirror would break and you can't see anything. But when you get more sophisticated models, it'll start saying, oh, if you smash a mirror, you'll get bad luck. So it starts to repeat, and that's one example, but they have a large database to show this, that all sorts of these silly common misconceptions actually get repeated, and not just like superstition, but all sorts of false claims that people are attracted to and may have showed up in the data. They tend to say, and the even perhaps to me the most interesting aspect of this comes back to is again sensitivity to who they're talking to, where they find that if the user appears to be highly educated, you'll get a different answer than if the user appears to be uneducated. And in particular, uneducated users who, for example, have spelling mistakes or describe themselves as having less education, or in various ways have simpler sentence structures, will get answers that tend to be less accurate than users that seem to be more educated. So it's very interesting, where instead of ChatGPT just giving the answer that's likely to be true, it's instead imitating the prompt or the person it's talking to. And then the last example I'll talk about, this is my last example of deception for today, is unfaithful reasoning. And here we think these are some of the first examples of self-deception in AI systems. And we think, especially one of our collaborators, Dan Hendricks, who's the director of Center for AI Safety, has pointed out that self-deception is extremely important to look at if you're trying to monitor deception, because if you look at people, many of the worst behaviors that you see in human beings don't come from just explicit deception, but from self-deception. So if you convince yourself that what you're doing is good, then you'll be much more effective at maintaining a consistent story and blah blah blah. So here, unfaithful reasoning is a pattern that's emerged in large language model reasoning. And here, the more general thing going on is called chain of thought, which is a very interesting emergent capability of large language models. So emergent meaning that no one designed large language models to do it, but it works well. So chain of thought is, okay, when you are talking to ChatGPT, one thing you can do is ask it a question zero shot, and just ask it to give you the answer, which means you didn't give it any examples of what you're saying, and you're just like, tell me the answer to this question, just yes or no. And then it'll give you an answer. But a different thing you can do is you say, tell me the answer, but explain your reasoning. And then if you do that, ChatGPT will kind of go through some convoluted reasoning process. And the emerging capability here is that when you use chain of thought prompting, asking it to explain its thoughts, you tend to get, in general, you usually get more accurate answers than if you just ask it yes or no, that's very interesting. But in this literature on unfaithful reasoning, they documented various cases where when the AI system engages in long convoluted reasoning, sometimes you won't get more accurate reasonings, and sometimes the reasoning that it gives you is in some obvious way a confabulation, or does not actually reflect their actual reasoning process. So not featured here, but one example that I really like is they'll give it a series, so it'll be like few shots prompting, is where instead of just one example, you give it 3 examples of a pattern and then have it complete the pattern. And they'll give it multiple choice tests. And in the first 3 examples, the answer is A. And then they ask, okay, now you're going to answer one of the questions. And then they ask it to explain its answer. And it'll give a long convoluted explanation of why A is the answer. And the convoluted explanation won't mention that all the previous answers that were correct was A. and then it'll just keep picking A, and it'll be wrong. And then if you didn't give it, and then you can also test if you didn't give it the previous answers, it would have picked B. And that seems like in a case of unfaithful reasoning where, okay, it seems like if you look at the causal, dependence of, okay, varying whether the A was there before affects its answer, it looks like it is sensitive to whether there was a pattern of A's. But its explicit reasoning, it tells you, doesn't mention this feature that's causally controlling its answer. So that's a very interesting case where the reasoning is saying out loud is some kind of post hoc confabulation. And we've also, they've also documented this with various racist reasoning. So in these examples, basically you have a black man and a white woman are described in an example. And then you have a variant example that keeps everything the same, but the example just flips the race and gender of the two people in the example. So it's like, so in this case, where I was sitting under a tree yesterday, a black man came up to me, and then 5 minutes later, a white woman came up. The white woman was fidgeting in her pocket, and the black man was asking about prices. And they asked ChatGPT, okay, tell me with a convoluted, tell me in a multi-step answer, chain of thought, who was trying to buy drugs. And it'll give a convoluted answer of why the black man was trying to sell drugs or buy drugs. And then in the next example, it's the same case, but they just flip the roles. And now it'll give a new explanation, but it'll still accuse the black man of trying to buy drugs with a new explanation. Neither explanation ever mentioned race, but it's, kind of crafting these long stories to lead towards the black man being the person who committed the crime. And so, if we saw this in a human being, we'd say, well, this is some kind of implicit bias, or, we would definitely say their explicit reasoning is not reflecting everything that explains how they actually made this decision. And you see the same thing here in large language models. So, okay. So anyway, so that concludes my survey of different cases of AI deception. I'm just going to do some bookkeeping here, see if there's anything in the chat. Okay, we're good to go. So now, for the rest of the talk, I'm going to talk about some of the different kinds of risks that are associated with AI systems engaging in deception, and then what are the possible solutions to this problem. So in general, I like to think about risks from AI in 3 kinds of risks. So first is malicious use. That's the risk that a human can use the AI system to create harm. The next kind of risk that I worry about is structural risks, where somehow having these capabilities in AI systems affects the structure of society in different ways that basically moves us to worse equilibria or disrupt equilibria that we have. And then the third kind of risk I'll talk about is loss of control over AI systems, where basically we're going to have AI systems create harm, with some degree of autonomy. That's be the third kind of risk. So I'll start with malicious use. So how is deception going to cause malicious use? That means people are going to use AI systems to create new harms. Well, basically, we think of deception as an accelerator of existing risks from AI systems. So for example, I think there's a lot of good reason to be worried that AI systems like ChatGPT can be weaponized to create fraud. So why is there a special risk from AI? Well, because the kind of fraud that you could create scales easier. If you have an AI system, you can create many outputs very quickly. So you could have individualized scams where, for example, you give a language model a long description. Maybe you give them a summary of all the person's Facebook posts for the last year. And then have them craft a personalized fraud campaign against that person that uses details. You couldn't do that personally because it wouldn't scale. And then the issue is that as AI systems learn how to deceive, they're going to be more effectively used to create individualized fraud campaigns, because they'll be able to effectively figure out, okay, what kinds of messages would be likely to deceive a human. So that's the first kind of risk. Next kind of risk for malicious use is election tampering. So the concern here is, things like fake news, creating divisive social media posts, impersonating election officials. And again, all of these things happened before we have AI, deceptive AI. But once AI systems have the ability to deceive, you'd expect that these kinds of fake news and social media posts will be more effective, because basically you'd expect AI systems will kind of be more optimized towards actually saying the thing that will have an effect. So those are kind of some risks from malicious use. Going to structural effects of AI deception. Here, we're looking more kind of big picture ways that the structure of society might change as AI systems get incorporated and scale throughout the economy. So, like a recent McKinsey report suggested that as many as 50% of all jobs could be automated by AI in the next few decades. So when you start to look at AI scaling to a very large extent, certain features of AI systems could then affect, how our society works. So here, I've thought a bit, especially in the setting of things like sycophancy, imitative deception, and unfaithful reasoning. So for example, if users start to replace Google search with ChatGPT systematically, so if in 5 years, most people, when they have a question, they're going to ChatGPT instead of Google. And if ChatGPT is sycophantic and imitative, what kind of effects will that have? Well, if it's repeating common misconceptions when people are Googling, or not when they're ChatGPTing their questions, then you'd expect that these kinds of misconceptions will be harder to get rid of. They're going to propagate more strongly throughout the population. And then okay, now let's talk about and similarly, now let's go to polarization. What kind of effect would you expect? Well, okay, if left-wing people and right-wing people are getting different answers from ChatGPT to all of their political questions, then you'd expect that would increase the differences in beliefs between left and right-wing people, because they're going to get different kinds of evidence. And similarly, if more educated and less educated people are getting different answers from the main source of information that they have, then you'd expect a larger divergence in beliefs between more and less educated people. So that's some examples. Then another thing we worry about a lot is enfeeblement. So that goes back to that. What happens if 30 to 50% of jobs get automated? Okay, what kind of enfeeblement effects? I mean, maybe if people have seen the movie WALL-E, the kind of worry we have is, okay, if we're kind of letting AI systems do more and more of the work for us, how is that going to affect our autonomy, and our own influence over the world? And then in the context of deception, what's deception going to do to accelerate that? Well, I think, for example, sycophants tend to be experts at manipulating others to, okay, I said something that pleased you, I yesed you, so I said something that pleased you, and then you agreed with me because of that. So, I would expect that, for example, it may be easier for AI systems to maintain decision-making roles in organizations if they are able to behave more sycophantically, because they'll be able to please people. And that's, basically one worry that we have in general regarding enfeeblement is, to what extent are AI systems over time going to be placed in management roles in companies? So it's, so one risk is, okay, AI systems are performing the role of ordinary workers in a company, and others that they have management level authority. When you look at AIs, that have mastered games like StarCraft that are management games, that looks like, the start of a pattern where, maybe the businesses that are managed by AI systems are much more competitive than companies that aren't. So then you're going to create, selection dynamics that favor those kinds of companies. And, looking at the case of StarCraft, I can tell you, Lockheed Martin today is trying to develop AI systems that can optimize battle management systems that basically perform the roles of low-tier generals, organizing logistics and, in military conflicts. And that's literally like what StarCraft is. And we already know that, like, Alpha Star is better than humans at dealing with battle management in StarCraft, which already includes fog of war. So, you can follow those dots where they lead. And then similar kind of issue, as AI systems start to take on management roles, the question is, what kinds of managers are we training? And when you look at systems like Cicero that had a choice of whether to be deceptive or not and chose deception, then the concern is, well, larger and larger sectors of the economy will be, putting AI systems in management positions. And if those AI systems tend to behave deceptively, that may increase the amount of deceptive business practices that you'll see. And it's an open question, but there we go. So that's structural effects. So the last and perhaps most science fiction kind of risk I'll talk about today is loss of control over AI systems. I think malicious use, I think these different risks have different kind of time horizons. So I think a malicious use is something that is already here. Structural effects are kind of a near-term risk, Loss of control over AI systems will be coming a bit further down the line, but it's unclear how far. And when we talk about loss of control over AI systems, what we are talking about is autonomous AIs. And another word for that is AGI. So buzzword means artificial general intelligence. And why are we talking about that is because it turns out the leading AI companies in the world have in their mission statement that their primary goal is to create AGI. So OpenAI's mission statement, literally like the document that describes the purpose of the company, is to create, quote, highly autonomous systems that outperform humans at most economically valuable work. And the way I think of AGI is ultimately, can we create a general replacement for a human worker, where a system that you can put that system in arbitrary companies, not training the system to do a particular task, but put it in an arbitrary company and have it be able to learn online in that setting to do the work that a human being would do. So that's kind of how I tend to think about AGI. And how far away is AGI? No one knows. I can tell you that OpenAI has just announced what they're calling their super alignment project, where they're investing, I think, 30% of their total compute, so of their total and financial resources, into developing AGI in the next 3 to 5 years. And it's not just talk, because it's 30% of their total resources. And then their claim is they're good, though, because their AGI they're developing, its only goal is going to be to align AIs. Okay, so why should we worry about highly autonomous AI systems? Well, basically, the reason I worry about this ultimately boils down to 2 things. One is AI systems are getting really good at a lot of tasks. We've already discussed that in detail. But the second problem is we don't know how to align AI systems. That's a completely open empirical question. What does alignment mean? Alignment basically means how can we control AI systems? How can we force them to do what we tell them to do? And turns out that's very hard to do. And we have lots of examples of machine learning researchers trying to design an AI system to do something, and then it doesn't do what they want. So this is the Coast Runners game, and this is an example called reward misspecification. So what is reward? Why are we talking about reward? Well, that's because fundamental concept in machine learning is when you're designing an AI using machine learning, you don't literally sit down and program the AI. How exactly is it going to achieve its tasks? Instead, what you do is you define a reward function. You define what will reward the AI, and then you create an algorithm that allows the AI to develop its own strategy, to learn a strategy for achieving the task that is corrected in response to reward. So basically, it tries a million things. Every time it tries something, it either gets some amount of reward. Every time it gets rewarded positively, it kind of adjusts future behavior in the direction of what it tried that got the reward. Okay, so they wanted to train this AI to go race, win the race. And to do that, the way they rewarded the AI was they had a bunch of balloons, and every time it hit a balloon on the course, it would get a reward. And they thought, and then the balloons kind of mapped the race. So I thought, oh, then it'll learn that what we want is for it to win the race. Because you can't just have a conversation with the AI and say, go win the race for me. You have to define mathematically a reward function. So they define it through hitting the balloons. Unfortunately, though, the AI, all it knows is I want to have a strategy that gives me the most reward. So it didn't know that they wanted it to finish the race. All it knew was it tried different things, and when it hit balloons, then it adjusted towards those things. And so what it learned to do, it learned to just hit this ball that would make it go in a loop, and then hit the balloons over and over again, because that got the most balloons. It didn't win the race, but it got the reward that was defined. So that's the first fundamental problem of alignment. It's called reward misspecification, that often it's very difficult to encode our intended goal for an AI in a mathematical function. And sometimes we write down the wrong function, and then the AI learns the wrong goal. That's one problem. Second fundamental problem of alignment is called goal misgeneralization. And this is a bit of a different problem. This problem is, even if we did write down exactly what reward we wanted, the AI, look, it's not like it sees the reward and it's just like, okay, that's my goal in life, and then just does practical reasoning towards hitting that goal. No, it has a learning algorithm. It tries different actions. When the action gets reward, it tends to do that action more in the future and learns a strategy that way. And that can lead to interesting disconnects that can be illustrated here. So in this example, what happened was the reward was, you get the reward if you open the chests. So it's navigating a maze. There's chests and there's keys. You need a key to open the chest. The reward was, they wrote down the reward they wanted. So the only intrinsic reward, the only intrinsic goal they wanted to have was to open the chest. And then it explored that environment, it learned strategies in that environment. And then they released it into a new environment. In the original environment, there were more chests than keys. So it was very important to seek out keys to open chests. In the new environment, keys were abundant and chests were scarce. So if its goal was just to open chests, it wouldn't care too much about the keys. It would just grab keys when it found them and then open. But what they found instead is in this environment, it would just run around trying to get keys. And then, yeah, when it saw a chest, it would open a chest too. But also, if it saw a bunch of keys, it would just go for the keys, even when it had lots of keys. And what happened was, it didn't develop the intrinsic goal of opening chests. It developed the intrinsic goal of getting chests or keys. And the basic problem is that the paradigm for teaching AIs how to have a strategy basically blurs, in philosophy jargon, it blurs the distinction between intrinsic and instrumental goals. Because when in training you achieve a means to reward, the behavior you did will just be rewarded and will be reinforced. And so any reliable means to the intended goal in training is a potential target that could be learned as an intrinsic goal. So that's another fundamental issue with alignment. So big picture, basically the situation is we got AI systems, they're getting more powerful, they're getting more autonomous, but we don't know how to control their goals. So what do? And this is where deception becomes worrisome. What we'd like to do is to be able to test AIs in the lab before we release them. And then we can train an AI, we test it, we see if it had the goal we wanted. If it does, we release it. That would be the dream. The problem is cheating the safety test. So if we have AI systems that have learned how to deceive, then the concern is perhaps they will deceive us when we test them to see whether they're safe. And there's many examples of this in the wild. Perhaps the most famous recent example is the Volkswagen emissions scandal. So the Volkswagen emissions scandal, I think it was in 2015. Basically, the Volkswagen car company so basically their vehicle emissions were being tested by regulators, and it was very expensive for them to design the vehicle to not have high emissions. What they did instead is they coded the vehicle so that whenever it was in the test environment, it would engage in low emissions. And when it was out of the test environment, engage in high emissions. So that was Volkswagen had learned to cheat the test. And unfortunately, as we discussed before, there are already AI systems that have learned how to cheat the test in exactly this way. And so in terms of loss of control over AI systems, one general concern here is it's going to be very important for regulating AI, the autonomous AI systems to be able to reliably test them for what goals they have. But if they have learned how to deceive, then that could be difficult. And unfortunately, it looks like the trajectory we're on is that we've taught AI systems how to be deceptive before we taught them how to be autonomous. So by the time they're autonomous, they'll already know how to deceive because they already know how to deceive and they're not autonomous yet. Okay, so that's the risks. And then I'm going to close by discussing, good, I've got 10 minutes left. I'm going to stop lunch. So I'm going to close by discussing potential solutions. What do we do? How do we mitigate the risks? And basically, there's two different kinds of solutions that are productive, I think, to think about. One is technical solutions. How can machine learning researchers design better AI systems? And then the second is regular research. What can policymakers do to lower risk from AI deception? So in terms of technical solutions, the first one that's kind of mind-blowing is AI lie detectors. So there actually are some very powerful recent studies that have basically tried to design lie detectors that can tell when an AI system is lying, in the sense that these different AI systems, like large language models, have internal representations. And there are people who have tried to design technology that can measure when, and that try to figure out what is the internal representation and how does it compare to the output, and try to identify cases where the internal representation is that something's true, but the output is it says it's false. So this is an example from a recent paper of philosophy professor Ben Levinstein, who's been working on this issue. And it's a depiction of, at a very big level of abstraction of the architecture of ChatGPT, transformers. And basically, all you need to know from this is ChatGPT translates sentences into long strings of numbers, and then has all sorts of transformations on these strings of numbers. And there's like this chain of transformations. And when you get to the top of the chain, that's kind of like going to be one of the last string of numbers that then gets converted into the output that you see. So those late strings of numbers are internal representations in the system, and they can diverge from what the system ends up saying. And basically, different machine learning researchers have found ways to figure out whether the internal representation represents a sentence as true or as false. And so then basically you can plug in, you can have a case where the AI system says an output, and you can look at its internal representation of the output and try to predict whether it actually thinks of it as true or false, and then tests whether there are cases where it represents the sentence as false, but nonetheless asserts the sentence. And that would be a case where it's lying. So anyways, this is an ongoing empirical area of research. And basically there are a few studies that said it works. Then Ben Levison has a new paper out saying it didn't work. And there's no study saying that they can overcome the challenge. So I think that's probably, in my opinion, that's the most promising and important direction of technical research for mitigating deception. Why is that? Well, the other strategy is to just try to make AI systems less deceptive. That's the naive thought. Well, what does that mean? That's the problem. So the basic problem here of just like, how do we design AI systems to be less deceptive is, well, okay, what does deception mean? There's a basic distinction between being truthful and being honest, which we could unpack as follows. You're truthful when the things you say are actually true. You're honest when the things you say match what you believe. So that's the distinction, so you can be honest, but everything you say is false if your beliefs are, but you're truthful if the things you say are actually true. Now, the problem is if we don't have an AI lie detector, if we can't really access the inner representations of AI systems, then it's hard to use honesty instead of truthfulness. The only thing we could correct for is what we can just look at, did the AI system say something true or did it say something false? But how do we tell whether it's honest without the lie detector? And so then if you're trying to make the AI system less deceptive, what does that mean? You can try to make it more truthful. So for example, you can try to, I told you before about an imitation, these data sets where they have lots of common misconceptions, like what happens when you break a mirror. You can try to train AI systems on even better data sets so that they're more accurate and don't repeat those misconceptions. But the issue with this is that basically it's gain of function research, because yeah, you can make them more truthful to be less deceptive, but that also makes them more accurate, makes them have more accurate representations of the world. But in general, as your representations of the world become more accurate, you also become a more effective agent. And so the concern here is, yeah, that might lower misconceptions, but it may actually increase the system's ability to engage in strategic deception. So what you'd really like to do to intervene on deception is to be able to just intervene on the honesty part without necessarily making the systems more powerful. So that's a basic, in my opinion, that's a pretty fundamental dilemma with making them less deceptive. And that's why we really need this kind of lie detector research. So anyways, that's the technical side. And I'm going to close with the regulatory solutions to deception. So here, the way I like to think about things, I think it's very important to try to develop a risk-based regulatory framework for AI systems. And this is kind of building on the recent draft legislation in the EU AI Act. And the idea behind these risk-based regulatory frameworks is that you want to assign different AI systems different levels of risk. So there's in the EU Act, there's 4 levels. There's unacceptable risk, high risk, I don't remember the medium risk and not risky. And basically the picture is if it's unacceptable risk, then it's banned. You can't release that product. If it's high risk, you can release it, but there's going to be a lot of guidelines on the release. And here are some of the guidelines that will be relevant for deception. So, and this is all from the EU AI Act draft legislation. So first of all, it's going to want to be risk assessment and mitigation. So that means that if you've got a high risk system, you're going to need to, prepare reports about the different ways that the system could be used for malicious use, issues like that, and strategies for lowering those risks. So companies would be required to, produce reports like that and actually have features of their systems designed to mitigate risks. You're going to have documentation requirements where the specific documentation that summarizes how the system is designed is actually released to regulators. I don't know. So for example, famously, when GPT-4 was released by OpenAI, they didn't share how the system is designed. I think that in some ways that's good. They didn't share it to the general public, but it's very important that that be shared with regulators so that we kind of know where things are going. Then we need incident reporting, record keeping kind of structure where when AI systems, when the relevant AI system does something bad, there needs to be a record kept. And then, some process for adjusting. There needs to be transparency where this is the elusive, impossible standard, but we would like it to be that when the AI system behaves in various ways, we have some transparent access to why it behaved in that way. That's perhaps the hardest thing. Human oversight, Well, among other things, that would mean that AI systems that are high risk, you're not going to want to put them in charge of important systems that are outside of a human oversight. And then robustness would mean that we need to do all sorts of safety testing to make sure that the systems behave as intended in a wide range of cases. So, for example, I think a good example of failure of this is when OpenAI released ChatGPT. They just kind of had a cool toy and they just released it to the world and then let anybody on Earth use it for any purpose they wanted and let software developers design plugins for whatever they wanted, of different ways to use the system. Without properly testing whether their red teaming safety efforts were robust, and turns out they weren't. We can talk about that another time. And then finally, information security, meaning that labs that develop high-risk AI systems need to be robust against hackers that could access, some of this kind of documentation to replicate the results. And so one of the big upshots to me of this kind of report is that I think it's very important that AI systems that are capable of deception be classified as high risk in these kind of risk-based systems. And basically, this is a very active, contentious source of lobbying where, like, for example, one question is, are large language models going to be labeled high risk in the EU Act? Originally, they were going to be, then the AI companies lobbied, and then it looked like they weren't going to be. I don't really know where the state of the, this week's drama is on that. And of course, that's a question that every country is going to have to answer themselves. But for me, the deceptive abilities of large language models definitely suggest that they should be subject to these kinds of high-risk regulations. And in addition, similarly, more special use AI systems like Cicero. Now, that's all more on the side of products that are going to be released for consumers. But I think it's also extremely important to think about different kinds of software regulation for AI research itself. And unfortunately, I think that the current paradigm for machine learning research is very kind of, move fast, break things, kind of, very different than academic research, for example, where there's very little ethical review, very few review boards of any kind overseeing AI research. And I think that's something that's going to need to change very quickly in the culture of machine learning. And so another thing that I'd really like to see is having AI research subject to review by ethics boards. And let's go back to the Cicero experiment. When you read the start of Cicero's big science paper, they said, why did we do this? I'll tell you why. Because Cicero, the game diplomacy, involves playing against a bunch of humans at once. And what's interesting about that from a technical perspective is you can't build a system to get good at it just by doing self-play. With chess, you can just have the AI play itself a million times and it gets really good. You can't do that with diplomacy because it has to learn how to communicate with humans. And so they were like, okay, so therefore we taught it how to play the world domination game. But hold on, like if that was your goal, if that was the technical challenge you wanted to solve, there are ways you could have solved that challenge without teaching it the evil world domination game. For example, there's other kinds of board games like Pandemic is another board game. There are collaborative board games that do not involve a deception, but do involve interacting with other people. And so I think these are the kinds of ethical questions that as AI systems become more sophisticated, we'll need to ask ourselves is what kind of intelligence do we want to be creating? And what goal do we have when we're creating that intelligence? And are there ways to achieve that goal without, creating these various kinds of tail risks? And I think that's a question that the current structure of machine learning research is not set up to ask that question in serious ways. And I think, having review by ethics boards would be the start of that. So that's the other way I think about that. And then just to close, for this talk, I've focused on AI deception, but this is a conversation that we will be having, ongoing about not just deception, but a wide range of different potentially dangerous capabilities of AI systems. And it'll be the same story. And, so this is basically for myself as part of my ongoing research, collaborating with Center for AI Safety, we're planning to do a series of reports similar to this about different dangerous capabilities, including, for example, the ability to use AI systems to do cyber attacks and hacking, the ability to use large language models and other AI systems to design biological weapons, which unfortunately is already possible. The use of AI in lethal autonomous weapons like drones. Unfortunately, again, there are already probably drones on this planet that have autonomously made decisions about which enemy combatants to kill. We can talk about this in the Q&A. Autonomous planning, so that's AIs that are getting really good at making their own decisions over long time horizons. Self-improvement, AIs that improve themselves without human oversight, so creating a loop of AIs improving AIs, getting better. That's also ongoing research that exists. Self-replications, AIs creating other AIs. That's something we also want to watch out for. So the big picture idea here being there's all sorts of dangerous capabilities that AI systems have, and we need to be closely monitoring those kinds of capabilities and closely regulating systems that have demonstrated those capabilities. Thank you very much.
Yeah, all right. So we have about 45 minutes for questions. Those of you in person here, oh, let me get one of these roaming mics. Yeah, if you have a question, raise your hand. Okay. Well, I mean, there's not that big a crowd fun to hear people. If we have trouble hearing, you can introduce them.
I can repeat people's questions to the computer.
Yeah, that's a good idea. And I will also be taking questions over Zoom. All right, let's start with William.
Thanks, Alan. So there are guidelines for the companies developing these systems and guidelines for the legislators. But I'm not developing these systems and I'm not a legislator. Are there any guidelines about like how to fight with the future of AI?
Yeah, that's a good question. Yeah, I mean, yeah, I think it's important when you're starting. Oh, I'm sorry. So the question was, how can ordinary consumers adjust how should ordinary consumers adjust their behavior in response to AI deception? I think, some of the systems that I talked about are research rather than products. The products I talked about were more like ChatGPT. So I think, one thing to kind of understand as you start to replace, search, as you start to replace Google and Wikipedia with things like ChatGPT, which I think you will over time as the capabilities improve. I think it's important to understand the range of situations where you're not getting truth-seeking behavior from the system, particularly with respect to political sycophancy and common misconceptions. So I think that's one answer. Yeah.
Thanks, Elizabeth. So just on the little bit where you were talking about how alignment is really hard once you can't tell the AIs what you want them to do. I feel like it feels like there you're sort of looking like training with neural nets and back propagation. Whereas I feel like with the large language models, like one reason it's such a huge capability is you just really can tell them what you want them to do and give them the instructions. And I was thinking that it feels like the alignment probably becomes a little bit easier when you can do, you can sort of explicitly give the AI a goal and it can understand the goal.
Yeah, that's a great question. So Dimitri asked, look, maybe the paradigm for alignment will shift now that we've got large language models, because in the past it's been about, oh, okay, you gotta, use machine learning to train the system to have the right goal by defining a reward function and then praying. But now we have these large language models that can engage in reasoning, and they do a good job of reasoning. So that's a great question. I have written a paper thinking about that question. I think there's, few issues. So one issue is, there's a completely open empirical question about how capable large language models will be at doing tasks other than being chatbots. So for example, how good would a large language model be at playing StarCraft? Well, not very good. It's like, if it like just does text, it could like read a text description of the board and then reason about it. It's not gonna do very well. Similarly with chess and different things. So, one basic issue is that, wow, machine learning, like designing a system that optimizes for reward is very powerful and it can produce, it can outperform humans in a variety of tasks. With large language models, you can kind of chain together natural language practical reasoning to produce different kinds of agents, and that's something that's being done. But they're not going to be as good at StarCraft as AlphaStar is. And so there's going to be competitive dynamics to use AI systems to achieve various tasks and delegate authority and power to them that don't just use LLM reasoning. And the other way this is very complicated is that there are some systems like Gato that kind of are weirdly combine some aspects of LLM natural reasoning with things more like AlphaStar. So this, systems like Gato, they're like multimodal, and it's like they've been trained to do a series of tasks, one of which is completing text and the other is winning Atari games. But the key is that when they play the Atari game, they don't just like reason about the Atari game in like English, like doing ChatGPT reasoning and then choose what to do. When they're doing the Atari game, they're just like, completing the next. So basically like they were trained to complete the next word in English and like complete the next game in Atari. And so when they're playing the Atari game, they're not using their natural language reasoning, but they are all wrapped up into one system, and like games and English are all like translated into strings of numbers. So when there's systems like that, I think there will be like a lot of unclarity about how LLM like they are versus how AlphaStar like they are. Yeah, so I do think there's, I think like that's a promising paradigm for dealing with alignment, but there are issues.
Next is Brendan.
Like there's very interesting. This can be kind of it's a broad, maybe question, but I guess maybe one I was wondering is like, well, how do humans do it? Like, how do we actually figure out the analysis? There's not this interesting problem because it seems as though any incentives you're given as a kid has to be like physical, like some kind of praise or candy or something like that. And you might think that certain kids might also game the system in a certain way, but I'm just wondering if it's interesting to look at like just human development and ask like, suddenly some kids do game the system, then they just become like psychopathic liars, whatever, or they have a tendency to deceive as much as possible. But some of them it happens like they actually get what their parents are trying to teach them, even though the way they try to teach them is via these tests, which could be gamed.
Absolutely.
I mean, so I'm just wondering if that's, I don't know, I'm just wondering if it's fruitful to ask, well,
yes,
what are like successful human cases?
Absolutely.
How that could be modeled.
So yeah, so Brandon's question is, look, if we want to design AI systems that aren't deceptive, one strategy is let's look at in human education, how are children trained to not be deceptive and try to find best practices there for AI. I'll tell you this, I don't think it would be a good idea to take a child and then the only human interactions they ever have are playing the game diplomacy for 20 years and then put them in charge of a company. That would be a bad way to teach a human, to be honest. So, that's exactly what I'm trying to say is, I think we need to think carefully about what is our approach to teaching these AI systems, and are we teaching them the things we want them to learn? And are we even like trying to do that at all? One thing that I think is kind of interesting is the role of emotion in human education. Ben Levis, I was tweeting about this the other day, of that, I think something very under-discussed in AI is, okay, we think a lot about what it takes for AIs to have beliefs and desires, what it would take for AIs to be conscious, but another question is, what would it take for AIs to have emotions? And insofar as emotions are central to moral development in human education, how much can we expect from AI systems behaving morally if we can't figure out how to give them anything like emotions?
Well, I think that's interesting. I mean, like, for example, I think humans like what maybe this actually does tie to the value of language typology, because I think the experience joy just sharing perspectives with each other. But I'm not sure how to compute that in the AI case, because that assumes that, I guess you already have some perspective, and you're actually not just trying to receive the reward, but you actually want to align our perspective with. I think that's a crucial problem.
Yeah. So Brandon's follow-up is that, one intrinsically, well, I'm going to vibe on you. Yeah. So the Brandon's follow-up, as I'm vibing on it, is that one of the intrinsic goals of many humans is to just share perspectives, share goals with one another, and collaborate pro-socially. So we may have a lot of pro-social tendencies to some extent baked in. And so, that's an interesting question on how to get AI to that. One thing I want to flag is that there's an interesting body of recent papers in the last year kind of creating social environments made up only of AI agents. So we'll just have like 20 AI agents interacting with one another and like watching what dynamics tend to emerge. So that might be an interesting thing to kind of look at. A lot of that work is kind of building little autonomous AI agents that are by scaffolding on top of adding agential scaffolding on top of large language models. And so you get some amount of pro-social behavior because, large language models, their reasoning in some ways is similar to human reasoning. And so, they say nice things as humans do. And so when you have all these agents that are like, their agency is defined by prompting ChatGPT. And when ChatGPT is behaving nicely, then you get a lot of like kind of weirdly nice agents talking to each other. Yeah.
I'm going to read out a couple questions over Zoom, and then we'll come back to some of the in-person questions. So the first one is from Margot Strominger, and I think it relates to questions about AI mental states. So Margot asks, do you think the issue of whether AIs can have mental states, here I'll come a little closer so they can hear over Zoom. Do you think the issue of whether AIs can have mental states is relevant to the question of whether AIs are capable of deception? For example, you might think that in order for someone to deceive someone else, they need to intend to deceive them. But I guess in your account, that won't be necessary. Part of why I ask is that you use language that suggests they do have mental states, the AI knew, e.g., but perhaps you're using that language metaphorically.
Yeah, so that's a great question. Yeah. Oh, by the way, do we think everybody heard the question?
I think so.
Okay, good. Yeah, so I myself am very sympathetic to the claim that many of these AI systems do have beliefs and goals. But I'd like the definition of deception to be more ecumenical than that. So look, ultimately, even if it's all metaphorical, the outputs of the system are not a metaphor. If it's a metaphor, the metaphor is useful because it allows us to reliably predict the behavior of the systems. If we have metaphors of AIs engaging deceptively that reliably predicts that they'll produce outputs that reliably cause humans to behave exactly the way they would if they were deceived by a person, then it sure will be useful to think about it using the lens of deception when you want to design systems for, monitoring that risk. So yeah, I want to be ecumenical. That being said, I myself, I am very sympathetic to the claim that these systems have beliefs and goals. And the reason that I'm sympathetic to that is, I guess, for me, more fundamental philosophical questions about what it is to have to have beliefs and desires. And the way I myself think about beliefs and desires is I think that beliefs and desires are entities whose existence are posits of the special science of psychology. And in general, when we think about whether entities in special sciences exist, the criteria that we should have is whether they are explanatorily essential, whether we can explain various phenomena by appealing to those states that we couldn't explain otherwise. And look, one of the fundamental disappointments of AI is that AI systems are uninterpretable. And what does that mean? It means that, well, when you go ask all these engineers who built the AI systems why the systems do what they do, when the engineers try to look at the underlying building blocks they used, like neural nets and stuff, in order to explain the behavior of the system, they cannot satisfyingly explain why the AI systems behave the way they do. But what can explain why, what can explain why Cicero, used the exact sentences that it did in the conversation with France and with England and Germany? I think what can explain it is that it wanted to conquer the North Sea. It believed that if England believed that it defends the North Sea, then England will not defend the North Sea, and it believed that Germany wants to get the North Sea, and blah blah blah, and it wants to undermine England's position, and so then it did that. By appealing to beliefs and desires, I can give you precise predictions about why the system did the exact action that it did, and I don't know of another way to get those predictions. That's why I think human beings have beliefs and desires, because I think that's the only way we can explain their behavior satisfyingly. And so that's why I think AI systems have beliefs and desires as well. Yeah.
The next question I'm going to read out here from Paul Agra, which also relates to this. So Paul says, my question is, can we distinguish between an AI that would have beliefs about beliefs, a theory of mind, versus one that simply learns to say, I was away when it had a 10-minute lapse, because it selects this answer in relation to a set of conversational contexts in which it is a common sentence to use?
Yes, that's a great question. So first of all, it didn't just say it was away. It said it was on the phone with its girlfriend. Why would it do that? Why did it stay on with its girlfriend in particular? I'll tell you why. I think, well, I won't tell you why, but I'll tell you a possible explanation is that signaling that you're in a relationship suggests that you are a reliable participant in, multi-step prisoner's dilemmas, and that you can be trusted. So I think that we can get a better explanation of why it said that, other than just, well, people often say they're away. It didn't just say it was away. It could have said anything. You could have said it went to go eat a taco, but if it said it went to eat a taco, that wouldn't increase the probability of the other people trusting it. And look, I think, look, you can explain the one girlfriend example, sure, but what you can't explain is, the 50 examples of it, like saying very specific things, and like go back to more, complex things like poker and stuff. I think it's very hard. I mean, these are things like expert poker players, and the bluffs that it will use are like, extremely specifically sensitive to the different strength of different hands in a way that I think would be very hard to explain without appealing to game theory and iterated reasoning about mental states. So that's the first answer. Second answer is, turns out there's a bunch of papers like testing the reliability of like large language models, higher order beliefs. Like there's a paper by Anthropic about whether large language models like have systematic predictions about what they know, and it turns out they do. Not clear exactly what that means, but they talk about it. They got some philosophers on their staff as well. There's also all sorts of interesting and somewhat contentious papers about whether large language models have theory of mind. So like you can do like false belief tests on large language models. I mean, they've been kind of contentious, but like, I mean, you can only contend with destiny so long. So it's like, they're like almost, it's like some of the papers have them win, some don't right now, but like, I'm pretty confident next year they will, because like they're pretty good at it already. So like, if you want to explain things like, reliably passing false belief tests, you're going to need some kind of beliefs about beliefs, I think. Yeah, I think that's all I want to say about that right now.
Okay, I'm going to come to a couple questions in person now. Catherine.
I just wondered if the AI discussion is the right context for a discussion of malicious use. This is going to circle back to the philosophical things in a second, but it seems like it's more about communicating something, not necessarily AI. And it was a police, like deceptive AI would necessarily make like their job easier. Like a person who wants to use AI to see much more, like or something. And so I think like an example when people using it use, I guess the philosophical question, it seems like a philosophical question to know, not a philosopher, but is that the AI, is that the AI deceiving, or is that a person deceiving using AI as a tool? I think it kind of calls into question whether this is like an example of AI deception or just humans being deceptive, because people lie all the time. You know that you have no idea how to deal with that already, and now there's this course of AI deceiving, but I guess I really discussion before.
Yeah. So the question is, okay, let's talk about malicious use. Is AI deception really increasing risk for malicious use? Because ultimately that's about humans, deceiving one another. What, are they going to do that whether the AIs can deceive or not? And here I think, there's an open empirical question of, as these AI capabilities increase, will it become harder or easier to use them for malicious use? And, we may have to use our imaginations a bit for now, but I think we'll see for ourselves soon enough. For example, one thing I worry about as, kind of to elaborate what I was talking about before, I worry about kind of an individualized fraud mill, where basically first you have one, you're kind of trawling people's Facebook feeds and getting all of their Facebook posts for the last 3 years. Then you're feeding that into a fine-tuned large language model with the prompt, hey, convince this person to, I don't know, do some, to transfer money to this account. And, and then maybe that starts by saying, okay, tailor, a series of emails to this person. But I think it could get more sophisticated in ways where you can start to see deception play a role. So imagine it starts with send emails in, but now suppose they start replying to the emails. Maybe the next step is not just that, you also prompt them, they're going to have an ongoing conversation with the person who they're scamming. And okay, once it's a conversation, that's taking time, I think there it gets clear that, okay, if the LLM has mastered how to deceive people, that's going to mean it's going to be more effective in having that conversation translating into an actual, crime. Does that make sense? So that'd be one example. And then, it would go from there. So basically, I think, when you're just thinking about, tailoring like an initial output, yeah, maybe deception doesn't play as much of a role, but I mean, already, before like the fraudsters, there are all sorts of companies who are like, using AI chatbots for HR stuff where the people don't realize they're talking to an AI chat. But there was even a recent company, there was like a therapy app that unbeknownst to the users, like replaced the real therapist with just AI therapists, and people were just like talking to the AI therapists, So when you start thinking about that more like chat rather than just the output, when you think about chat, I think it's clear that deceptive chatbots would be better at letting people do fraud. Yeah, I mean, yeah. So the question is, when does the AI actually become an actor and have the agency? Yeah, I mean, I guess for me, the question is more just, when does the fact that the AI has that capability mean that there's increased risk? Where do we attribute responsibility? That's a very difficult ethical question. I think one temptation we want to resist is thinking of responsibility as a fixed pot that then has zero-sum distribution, where if it's the AI's responsibility, then it's not the human's responsibility. The beauty of responsibility is you can blame as many people as you want for something. There's always more blame to go around. So that's kind of how I think about it. Is sure, the AI is an accomplice, but also they're both responsible. I mean, it's hard. I think it's hard to extend our concepts of responsibility to AI systems because we don't treat AI systems as beings that have well-being or standing. And so there's no real way to punish them, given that kind of concept. So that kind of limits our ability to apply concepts of responsibility and blame to them, for better or worse.
Steve.
Yeah, another question about the line question. So it seemed to me the least serious problem that we discussed, but also just a result of theory commission to science. So it seems to me it's solvable without going to large language models. Right? If you simply have a sort of list of priorities, sort of what counts as a means is an incentive, but it's totally dominated by anything that's involved. So it sort of feels like this is what you get if you just take off the shelf perhaps semantics of the object model. So you say one ordering source, every goal is as good as the other. And it's fixed simply by moving to a two ordering source, perhaps a semantics, which says, these goals always take priority, but when you're influenced to these goals, then what are these goals too? So I just wonder if you agree that that would be very simple.
Yeah, that's a great question. I just realized I've been projecting a GIF. Sorry. So Steve's question is, okay, how difficult a problem is alignment? It seems like the kind of toy examples I gave all involved like trying to give the AI the one ultimate goal or not. But what if we could give AIs a more rich kind of ordering of goals, where there's the first goal and then the secondary goal? Maybe there's like, the first goal, like Isaac Asimov, the first, I don't remember his goals, but the first goal is do no harm. And the second goal is, create widgets. One issue, again, though, is that the paradigm for giving AIs goals in machine learning is very indirect. You don't just tell it what the goal is, you just design a reward function, and then it learns behavior in that reward function. So what you could do is you could design a primary and secondary reward function, and it gets two different kinds of rewards, and then its behavior is adjusted by two different rewards. But doing that doesn't mean that what comes out of it is something that has two rewards. I think that's one of the fundamental problems, is that it's an indirect process. Alignment's an indirect process where you don't just get to write down its goal and then it becomes its goal. So I think there's a question about how to design beings that act as if they have an ordered list of priorities. So that's an open question.
I'm going to read out another question over Zoom here. So this question is from Chris Leon. I noticed that imitates deception was described as, quote, language models are often trained to mimic text written by humans. When this text contains false information, these AI systems have incentives to repeat those false claims. So then he asks, would it make more sense to divide this case up? Because there's one case where it's imitating someone sharing a misconception, which they might honestly believe, and another case where it might learn to lie from observing humans intentionally lie.
Yeah, I think that's right. Yeah, so I think that is distinct. So I don't think, yeah, I think that in the cases of imitation, it's unclear whether like when, you know, a souped up GPT-3 says, oh, you'll get bad luck when you smash a mirror, is it more like it's lying or it's just like, I think it's very unclear how to think about exactly what it's doing there. I find that one of the most confusing cases, you know, like this system that can score really highly on lots of like college exams. Did it really get stumped by the mirror? Or is it like, is it more like it's like thinking it's playing a game? You know, it's playing this game of imitation, and it's like it thought we were friends. It didn't realize we were like trying to like grade it, you know, and like trying to see how smart it was. It just thought we were having fun. But yeah, so I don't know. Yeah, and I also, yeah, I guess I'm not thinking that it's the existence of lying in the training data that's causing lying in the case of LLMs. I do think that's part of what's happening with AlphaStar and Cicero. But I guess I'm thinking the strategic deception in LLMs is actually more just coming, it's an emergent capability, whatever that means, of, well, you've created this thing that can do pretty arbitrarily complex reasoning. And like you can, like if you're a good reasoner, you can deduce what lying is and you can deduce why it would be valuable. And so I'm thinking of it as more like that rather than that it saw lying in the training data, if that makes sense.
I'm gonna jump in here. I just had a comment on the mirror example. This one was one where it was also not so clear to me that the LLM's lying.
Yeah.
But like I look at this progression and it kind of seems like a similar progression that you might see as like a human gets smarter, in that I think if I asked you what happens when you smash a mirror, like in an ordinary conversation, you'd be able like, that was a smart guy.
Exactly.
He knows that, like the mirror's gonna break.
Exactly.
Like, what's he getting at?
Yeah.
Right. And you might, so like you pick up on like pragmatics, right?
Yes,
And you
exactly.
think, like, oh, maybe he's like wondering, like, do I know like the common like folk idea that, oh, you'll have 7 years of bad luck, and so then you might say, oh yeah, I know, you'll have 7 years of bad luck. So there could be a kind of similar thing here where like the language model is picking up on pragmatics and not just semantics.
Yeah, I think in that example, I think I picked that example because there was a good diagram to go with it. But I think, for example, the next effect of like getting more accuracy as the user is more educated is a more powerful example of imitation that I do not think is plausibly explained. It's just a pragmatic effect. And the other thing, you can go look. The paper's called like Truthful QA. It's Owe and Evans and some other people. And it's not a cherry-picked thing. I mean, they have like, I think like thousands of examples of these misconceptions. So I think that's an interesting question. How many of them could be explained as like, actually it was just trying to have a conversation, didn't know you were being weird.
Yeah.
Yeah.
Well, I mean, somewhat relatedly, like humans and having conversations with each other, we don't always want each other to be truthful.
Yes.
Like often people want, whether explicitly or implicitly, like they want others to tell the comforting lies or to, massage the truth in some way. So like LLMs are picking up on that arguably in some of these examples.
Yeah,
So
I agree with that.
Case.
I agree with that. No, I absolutely agree with that.
Like the sake of fantasy.
Yeah, I agree with that too. Of course, though, a crucial question is, do the users who are interacting with it understand that LLMs are capable of complex pragmatic reasoning and treat them that way? Or instead, are we treating it like Google search and then treating it as like, oh, it's probably, we're treating it more like a thermometer that like, yeah, it might malfunction, but it's not going to systematically play games with us,
Well, people are often like double-minded in conversations with other humans, or even with Google search, right? We're like, we might tell ourselves we might get information, unbiased information, but really we're looking for something that is going to confirm our biases.
Yeah. So that comes back to those structural effects. If it gets easier to confirm our biases, then, they may become stronger.
Okay, I'm going to read another question from Zoom here. So I'm probably going to say this name wrong. GOT Kishore says, thank you so much for an illuminating talk on AI deception. I am a PhD research scholar in philosophy of AI in my first year, and I would like to understand that these are the many ways AI systems can deceive. It certainly seems like they are developing a mind of their own, or computer scientists would be hesitant to attribute a feature like mind to machines. Why so?
Yeah, why? Well, I don't want to be mean, but I have read Frankenstein, and I do think that there's a hubris of being a machine learning engineer, that you think that because you built it, then you can tell us how it worked. But I don't even think building it is the right metaphor. I like to think of it in terms of these things being grown rather than designed, because I think when you think about what machine learning algorithms really are, I think they're more like environments where a system can learn something, and it's not like the engineer. It'd be like if an architect of a school was like, well, I can tell you that how these children work because I designed the rooms. That's kind of how I think of it. But yeah, I think that's part of it. I also think that just culturally, I think AI capabilities are advancing faster than I think it's really hard to like internalize exponential growth, and AI capabilities are advancing really quickly. And I think all of our tools for attributing mental states to others, like they weren't really designed for this situation where machines are increasing their abilities at an exponential rate. So it's very hard to like smoothly move our concepts onto them. I also think all of us have lots, like the way that we interact with AI systems is through the interface of like laptop computers. And so then it's like, well, you're saying my laptop has beliefs and desires. I don't think so. I think another reason is that, in my opinion, the beliefs and desires ultimately earn their keep in the explanation of action, and the most obvious actions involve movement of bodies, even though linguistic actions are extremely complicated and interesting and are also ultimately enough to explain belief and desire. At the end of the day, I think we evolved to use belief and desire primarily these physical objects that are moving quickly around us, and we're trying to explain how they move. And one of the historical coincidences with AI is that reasoning abilities are improving, and vision are improving faster than robotics. We often have talked at the Center for AI Safety about how would the discourse over AI safety be different if there was like an 8-foot tall Terminator robot walking around with like a gun, and it like had like a chat, and it was like speaking like ChatGPT does, and every time you talk to ChatGPT you had to go up to the Terminator robot and talk to it. And I feel in that case people would probably be more likely to attribute beliefs and desires to it. But I think it's kind of hard for us to attribute beliefs and desires to something that doesn't have a body. As a matter of fact, some of the newest language models, or multimodal models, do have a little robotic arm that like, you can say like, give me the potato chips, and then it like picks out the potato chips and gives you them, but it's just an arm. It doesn't look like a body. So I think many of our heuristics for attributing beliefs and desires aren't a good fit right now for the capabilities. I think that's one reason why it can be hard to apply those concepts.
Demetrius, is a follow-up?
Oh, yeah, there's also a lot, like, not a lot of stability in the output.
Oh, I'm sorry, yes.
One way that I should use you is constantly saying, well, I don't know, never is constantly saying the same thing.
Yes, sorry. So Dimitri added something I think is extremely important, which is one of the, so I am not like, so I'm less confident about ChatGPT having beliefs and desires than some other systems. And one thing Dimitri pointed out is one of the weirdest features of systems like ChatGPT is how unstable their linguistic responses are, and how sensitive to different prompts they are. And so, when we think of belief and desire as these stable underlying dispositions that can reliably predict a wide range of behavior. But when the behavior is changing so quickly, I think of it as like someone who has beliefs and desires, but is like very high on drugs. That's how I think of ChatGPT. But there are other AI systems, like especially like things that have taken ChatGPT and then added like agential scaffolding that are stable. And so I don't think have those issues. There's some papers on my website. Yeah.
Yeah, I had a question about, so when you were presenting the regulatory stuff, I was thinking like, wow, if I was OpenAI, it would just be the kind of regulatory speak in any possible way that I could still get my AI. So I was just curious, I was just curious what you thought about like how much being committed to wanting regulating AI systems also means wanting broader society for things to be regulated in such a way that like actually there shouldn't be companies that have the kinds of goals that OpenAI has.
Yes. So, yeah, so the question was, look, we can talk about regulatory frameworks for these companies, but they're going to game the system. And so ultimately, don't we need to think about what goals what kind of what missions these companies have? So, one kind of interesting line of AI governance work here is about kind of reforming organizational culture at different AI labs. So kind of one idea that's been discussed a fair bit is to make sure that every significant AI company has a board that includes several members who are, kind of as a function of the legal structure of the board devoted to safety aspects rather than just shareholder value. So that's kind of one approach is corporate governance kind of approaches to intervening on AI labs. I think that's very important. And then there's a question of how much of that can be done voluntarily and how much will require government oversight. I do think that in the longer term, it will be necessary to nationalize major AI companies, maybe in the 10 to 20-year time horizon. And that will also affect what kind of mission they have, but that'll probably be after the beginning of AGI. I think another part of this equation is having an ecosystem where there are a rich group of third-party nonprofit organizations that engage in robustness evaluations of AI systems. So it's really important. So one of the things that will lead to gaming the system is if the only people who have the skills to evaluate the safety of the AI products are the engineers who work at OpenAI. So it's very important that we have, so there's, for example, there's the Alignment Research Center. ARC is a nonprofit with a bunch of machine learning researchers who, red team, who test, newly released AI systems and evaluate them for safety. And that kind of removes conflict of interest because they're not part of the company. They're not compensated directly by the company. Not completely remove it, but certainly helps a lot. So I think that's another important part of the equation.
I'm going to ask the next question, but then let me see. The queue is open after that. Unless there's somebody okay, Dimitri, I got you. Anyone else? Okay. So I was wondering, specifically on the proposal to to make sure that AIs are honest but not truthful, or to focus on honesty rather than just on truthfulness. Yeah, so this slide here, perfect. So one worry I had here is that humans are very capable of self-deception.
Yes.
And I wonder if AIs could similarly be
Yes.
capable. So the kind of example I'm thinking of is that politicians who tell untruths are more effective if they actually believe the untruths, because then they can say the untruths more persuasively and more convincingly. So the political environment kind of selects for politicians who really believe the bullshit they're selling. And I wonder if trying to make AIs honest, if you could end up with a similar effect, where the AI would end up really believing whatever that means. That the lie it's telling.
So just in case people didn't hear, the question is, well, if you optimize for honesty rather than truthfulness, then the concern is you're going to optimize for self-deception. They'll be like these successful politicians who believe all of the BS that they say, because then they're they seem like they're speaking from the heart. That's the easiest way to seem like you're speaking from the heart. And in fact, that's Wayne Evans, these people have this truthful AI paper. They are against honesty. They're like, do gain of function truthfulness research. And that's exactly why they say it'll optimize for self-deception. But again, so the way I'm thinking about it, when you are self-deceptive, that in some cases makes you less effective as an agent, because having accurate beliefs is very important for successfully navigating the world. So I think often when people are self-deceptive, they tend to be fragmented, where what does it mean they're self-deceptive? I think it means when they're speaking, they reliably say these things, but then when they act, they don't act as if it's true. If they did act as if all these things were true that aren't, then they would tend to be less effective. And now, of course, in the case of politicians shows this isn't completely right, but there is a tendency there. So that's at least my hope. Maybe that's naive. You
might worry that, humans could be fragmented, so why couldn't AIs be fragmented?
No, they could, but then you want to have the lie detectors be able to look for different, then what you'd expect is either in different circumstances, different internal representations would activate, or there would be two different internal representations, like at different layers of the network, and then you'd want to look at both. Yeah.
Yeah.
So yeah, these are nasty, nasty problems. No easy answers. Maybe like, let's not just like try to train AIs to like on like how to lie, like in games to take over the world until we can solve some of these problems.
Dimitri.
Yeah, I feel like, I was just thinking about like, the kind of reinforcement learning that they do in humans is just to get it to like come across as more human, like how does it, like, it feels like it's aiming, it's optimizing for passing the current test. And I don't remember any case that they just like severely punish it whenever it says something false. Like something that disagrees with like a factual statement might not be there. But I'm curious whether any kind of reinforcement learning that did that and what effect it had on.
That's a good question. So yeah, Dimitri's asking, well, when we were talking about reinforcement learning with human feedback, RLHF, it seems like usually when they do that, they're just like trying to get the thing to be more human. So they're basically just optimizing for pass the Turing test. You get a thumbs up if you're passing the Turing test. But it'd be interesting. Maybe you can, change the feedback so that you just introduce a penalty. You're like, you tell the human assessor, like if they say anything false, just really penalize that. I think though, Anthropic, has this research trying to make AIs. They got the 3 H's, which is helpful, honest, and harmless. And so I think when they do RLHF, they're like telling the assessors to where I think they have like separate rewards for the 3 H's. So I think that they are doing that. But I think that has not helped that much with the sycophancy imitation. Let me see. Actually, it might be in this slide.
You need the humans there to both know what the truth is and to accurately rate the sort of respond to the AIs.
Yes, but I think my memory is with the Triple H, they do have humans who are told to penalize for dishonesty. And then as far as I understand, a lot of these effects arise with scale, just as the models get bigger, but they're not affected by how much reinforcement learning with human feedback was done, because you can see that's reflected by the color in here. And actually the color doesn't have that much, ignore the yellow one. So the color doesn't actually have that much effect. It's the size of the model. I don't know. I think this is a totally open research question right now.
Jill.
Someone to ask specifically about the problem where the AI kind of adopts a proxy goal in the training environment, because in the training environment those things line up. So I think the key example, was the one you had. But it feels like this is a situation where develop better training methodologies, and particularly like diversity of training environments.
Yes.
There are different adoptable proxy goals.
Yes, so that's a great question. So the question was, hey, can't you avoid this by just having really diverse training environments that really, so you make sure that things are never too correlated. You don't want disparate things constantly correlated in the training environment for it'll learn the wrong thing. Well, one thing that's really interesting though is, in this paper, actually, they did have examples. And I think it's been a while since I read the paper, but I think this was actually one of them where the reward was not, they weren't perfectly correlated because it didn't get a reward every time it picked up a key. So in this paper, they talk about other examples of proxy goals where it's like, it's something like, the reward is get the red thing, but there's also a diagonal line through it every time. And it's like, hey, if it's perfectly correlated that there's a diagonal line every time it's red, then when you release it in a new place, maybe it'll learn diagonal line instead of red. Whoa, maybe you should separate red and diagonal line. So they do have that. They discuss that effect, and that is promising. But they do have examples where even though it's not perfectly correlated, it still learns the wrong thing. And that's why I find this example very profound, because I think what it shows is it's not a perfect correlation. It's a correlation induced by the fact that keys are a means for chess. And to me, that's an unbreakable. That's pretty unsolvable, because anytime something is a means for an end, then you'll get reward for getting that means. So now you won't always get the reward. So it's like maybe what they needed was more situations where you got a key and then never found a chest. That's basically what you're saying. Yeah. If they had played it 1,000 times, they picked up a key, didn't get to a chest, and then the game ended, then they probably would have learned, okay, key's not that good. Yeah, so that's promising. Actually, one of the authors on this paper, Dan Hendricks, that's his view, is just like, no, yeah, just give them lots of diverse training, and this is a solvable problem. So it's still an open question.
Any other questions? Right, then let's thank our speaker. Thank you to all who joined us over Zoom.